When we look at the sun from Earth, we see a solid-looking sphere with a sharp, distinct edge. But that crisp horizon is a clever deception of physics. If a heat-proof ship flew toward the sun, it would never hit a physical surface, only thickening gas. The sun's apparent edge is actually a transition in optical depth. This diagram shows how photons bounce randomly through dense plasma until they reach a threshold called tau equals 2/3. At this depth, trapped light flies straight into space. The plasma isn't heated to 10,000 degrees Fahrenheit by an external fire. Instead, the gas right at this transparency boundary is simply glowing at that temperature as it radiates its energy away into the void. This visible boundary, the photosphere, is only about 300 miles thick. In the context of a star nearly 1,000,000 miles wide, this layer is proportionally thinner than the skin on an apple. Despite appearing like a solid wall of fire, this layer is a near vacuum. The surface we see is actually thousands of times less dense than the air currently inside your living room. This razor-thin, ghostly mirage is the engine room of our solar system. The microscopic friction within this boundary is responsible for every major solar mystery and the destructive space weather events that threaten our planet. To decode the sun's mechanics, we rely on high-altitude observatories like the Inouye Solar Telescope, situated above the clouds on Haleakala in Maui. Through these massive lenses, the smooth solar disk shatters into 4 million churning convection cells. Each of these granules is roughly the size of Texas, boiling over on a cycle of just a few minutes. This isn't like water heated by a hot plate. Instead, the plasma is flash frozen from above by the cold of space. As it loses energy, the cooling material becomes heavy, sinking rapidly in dark sheets that outline bright rising centers. In August 2026, a technological breakthrough allowed physicists to see deeper into this process than ever before, resolving structures as tiny as 19 kilometers across, the size of a single city. Physicists discovered Kelvin-Helmholtz instabilities, tiny plasma vortices swirling and curling like breaking ocean waves along the granular boundaries. These 19-kilometer swirls reveal that plasma is constantly mixing and twisting magnetic field lines at the granular edges. This microscopic friction provides the initial kinetic energy that eventually scales up into the sun's most monumental star-spanning events. Beneath these visible granules lies the convection zone, a layer 200,000 kilometers deep, where energy moves through massive churning flows. This is the convection conundrum. Our computer models require deep, massive, giant cells to power the sun's magnetic field. Yet actual physical measurements show these flows are 20 to 100 times weaker than the physics says they should be. Moving upward reveals a second paradox, the coronal heating problem. Normally, moving away from a heat source makes the temperature drop, but just above the sun's surface, the atmosphere violently spikes from 5,000 degrees to over 1,000,000. One leading explanation is the nanoflare hypothesis. This suggests the constant bubbling of surface granules tangles magnetic lines until they snap, detonating countless microscopic heat bombs into the upper atmosphere. Alternatively, Alfvén waves might carry the load. Those newly discovered 19-kilometer surface swirls may act like twisting ropes, violently whipping energy upward from the photosphere into the corona. These unsolved paradoxes define the limits of our ability to predict solar activity. The invisible magnetic tangles born from these surface motions are the primary source of the storms that routinely threaten Earth's infrastructure. Where the magnetic field becomes thousands of times stronger than Earth's, it can physically choke off the churning plasma. These regions cool down and darken, forming the features we know as sunspots. As the magnetic tension in these sunspot regions reaches a breaking point, the fields rapidly rearrange. This sudden snap violently launches massive clouds of plasma and radiation outward into the solar system. A magnetic snap occurring in a near vacuum 93 million miles away creates a shockwave that slams into Earth. In May 2024, the extreme Gannon storm proved how powerful these events could be. It was the most intense geomagnetic storm in 2 decades, pushing vibrant auroras across the globe. The storm's interference knocked out precision GPS networks from Midwest tractors during the height of the planting season. In just one weekend, the resulting agricultural delays cost an estimated $565 million in losses. To defend against these costs, we use helioseismology to read sound waves trapped inside the star. By listening to how the sun rings, we can spot dangerous magnetic tangles forming on the far side before they ever rotate toward Earth. Decoding the optical illusion of the sun's surface is our only way to extend our warning systems from minutes to days. It is the key to protecting the hyper-connected infrastructure of our modern world.